Hello all, welcome to my channel. I'm back with a new video. In this video, we will go through cardinality and its impact on Spark's job performance, and we'll see how choosing the right cardinality for right columns helps us making a better pipeline. So let's get started. To start with, what is cardinality? So cardinality is basically number of unique rows or number of unique values present in a column. So there is a different cardinality as well, like in SQL database, we have cardinality like one to many, one to one relationship. So we are not talking about that. We are talking about cardinality in purest sense, where how many unique values are present in a column. And why it is important is because the cardinality actually decides how the data is stored, how it is distributed, and how it is queried. So if we choose the wrong column and wrong cardinality for joins or partitions, then we might see downgraded performance in Spark. So it is very important for a data engineer to know what cardinality is and how it is the hidden lever that makes or break the scalability. And so let's see how it impacts a few operations or few aspects of Spark job. So joins. So if we do a join on a column which is of high cardinality value. So high cardinality means there will be a lot of shuffle. And if we do a aggregate on, or let's say we are doing a group by on a column which has higher number of cardinality, then we will have too many unique values. So the number of groups that get created will be very high. So in that case, we will have a lot of intermediate data. This might also at sometimes might cause skew in while doing the join, because let's say if although we have high cardinality but one key has more data, then a skew can happen. So doing a, let's say if we are doing a group by on transaction ID, so transaction ID is going to be always unique, or always will have multiple very less repetitive records. Let's say it might happen that one transaction, one record can be for the transaction. For the same transaction ID, it can be for a refund. For same transaction, it can be a payment details and stuff like that. But overall, for one particular transaction, we won't have that many related rows. So it will create a high cardinal, it will behave as a high cardinal column, and that may not work out well. Rather than doing that, if we do it on the user ID, so one user might have done multiple transactions. So the number of records that get grouped into one particular user's bucket will be high. And what if we have joins on very less uh, or join on a column which have very lower cardinality? So what it will do, it will have many rows collapse in the same bucket. So we will have a skew. Plus, if we do aggregate on low cardinality numbers, so we will have huge one particular one particular worker or one particular partition will be doing a lot of work, because we will have lesser distribution of data. So generally for join and for this group by kind of work, we prefer for joins, we prefer high cardinality keys, because that gives us even distribution of data. And if we choose for group by, we choose low cardinality keys for roll-ups or aggregation, because that helps us in doing more work for a CPU. So this comes out as a summary of this. We can think is high cardinality distributes data well, but low cardinality concentrates the data, and hence based upon that we can come to the conclusion or come to a point which says high cardinality columns explode data size, while low cardinality columns explode compute. So if we have low cardinal numbers, then the data will be distributed more. So we will need more executors to process it, and hence we are saying that we will need more compute or CPU. Next comes partitioning. So In partitioning, if we have high cardinality columns based on which we do the partitions, then we will end up with lot of small files or lot of directory with very less number of files. It will create a metadata bloating, and we will not be having the right distribution, and the queries will be slow or queries will not run as fast as possible. So we need, if we are having low cardinality columns, a very low cardinality in partition column, then we will have hot partition, like one or two partitions will have most of the data. So the balance is to have partitioning columns cardinality in a moderate range. Let's say into let's say if we are dealing with a huge table, so it should be in the range of around 1,000 to uh, I mean, like in hundreds to thousands. So that should be the cardinality when we are deciding on the partition. Uh, Bucketing. So again, bucketing, if we have high cardinality column based on which we are doing the bucket, it will be it will be good for joins because the data gets evenly distributed across the buckets that we have. But if we have too low cardinality, then it will create skew. Again, here also we should aim for a higher cardinality columns for bucketing, so that the data is distributed on evenly, and the bucket count should be in a such a the bucket count should be in such a number that it balances both parallelism and the file counts. Then comes Z order. So Z order is as an optimization layout optimization technique which is used in certain lakehouse table formats. So this is based on that the data is co-located. So if we have a high cardinality column while we do a Z order on that column, so there will be not much of help because this can't optimize because the query pruning which won't escape files enough. So because Z ordering tries to place similar data in co-location, but if we have too much of cardinality, then that point of being closer to doesn't make sense. Same way it goes with low cardinality as well. There also it won't help. So we should have, uh, if we are trying to do a Z order optimization on a table based on certain columns, those columns should have medium cardinality, not too high, not too low, and that will help us in data escaping and pruning. Uh, then we have data skew. So as we mentioned, if we have low cardinality keys, the chances are there that we will have skew because if we have low cardinality keys, the keys are low cardinal value in number, so there will be lesser partitions and all the data will get fitted into lesser partitions, and hence it will cause overload or may result in a skew. But if we have high cardinality column, then data skew happening is very less because when the partitioning will happen, it will get evenly distributed across. But if the cardinality is too high, then we will end up with a small number of keys that can dominate, or we can have partitions which are processing too very less data, and hence we will be wasting resources in there. So the right thing here is to do a balance of for skewed data. Let's say if we are saying because of low cardinality we are getting skewed, so we can use salting or skew hint to fix that. But if it is for coming from high cardinality, then we can do histogram based partitioning or top end special handling that we can do to work ahead with data skew. I will create a separate video where I will discuss how we can do histogram based partitioning and top end special handling. So in summary, what we see is if we have high, it's like cardinality decides on how the data is spread. So if we have high cardinality, then the data distribution is good, but it is bad for storage because it will create too many small files. The partitions will be smaller and too many partitions will be there. But if it is low cardinality, then it concentrates the data. It will be good for bucketing and the stuff like, but it will bucketing or compression that will be good, but bad for data distribution because if we do partitioning or so it might create skewed partitions or partitions which has very high number of keys. So yeah, this was it for this video. If you like it, do share it. Have a nice day.